Today we're doing more math.
Your room is very bare.
Okay, yesterday we got distracted long enough. It's like 2:17. We don't have that long. That's why they can't put 8 at 7 period. My gosh. Let's see. Yesterday we were working on 6.2 and life got a little fuzzy. Hopefully today will be a better day. There's not that much left in chapter 6 notes wise. You notice we've got 1, 2, 3 pages. And so theoretically, we could do 1 page today, 1 page tomorrow, which is Friday, the last page Monday. We could review Tuesday, test Wednesday, and that would be best, I think. That way on Thursday, we could review for the semester exam. I think that would be wisest. So just so you know, chapter 6 test is going to be on Wednesday. Okay. If we were to do a brief recap of what's been going on lately, we started off with continuous and discrete variables and how to deal with their expected values and probability. And the good news is that the formula for the expected values and the variance for a discrete variable is actually given inside your formula sheet. So you don't actually have to know either of the formulas on the second page. Now, do you have to understand what they mean? Yes. But do you actually have to have the formulas memorized? No. Then we talked about how for a continuous random variable, life's not as nice. We actually have to find the area under the curve in order to deal with probability and expected values. It's here.
Oh, I was going to say, I just want to double check to see the super quick. Questions like where we have a certain, like an Apgar score or a situation like that, you said you do want us to keep the decimals or don't?
No, we were talking about we want to keep the best decimal with expected value. Apparently, they're going to count off, which you think they would understand I'm rounding down because I need to go to the nearest whole number. And maybe if I had specified that, they would be okay. But they literally want the 8.128. So you understand, yes, the expected value is not one of the given Apgar scores, but this is still nonetheless what we calculated. Seems redundant, but it is what it is. So, continuous random variables, we find the area under the curve. Hopefully it's a normal curve, so we can use our normal distribution or our z-table, something we've done before. But sadly, sometimes it ends up being something geometric, and we've got to find the area of the shape. The next section was, yes, here. It goes in the first period tray. Thank you. The next section we dealt with if we were going to transform stuff. And there were a bunch of looking formulas and really realized we don't need any of that. We just need to focus on the fact that the mean is not resistant if we add or subtract, whereas the standard deviation we're not going to add or subtract. So there was no big deal there. Finally, yesterday is when life kind of got a little fuzzy. If we were doing 2 variables at once and we wanted to either combine them or find their difference, literally we're just either going to add or subtract their expected values. It's not a big deal. And there's a formula for variance, but you have to have the phrase if they're independent. So a lot of the times they forget to say specifically they're independent, so you get to put, I can't do this, or like not possible because we don't know they're independent. So there is one formula we do need to know. So we've got 1 so far. Today we're going to add another one to that list. However, if you're not a formula person, then we're going to discuss other ways to know the answers. Okay, so today is 6.3. So we've bounced through 6.1 and 6.2. We're now on 6.3. And we're going to talk about binomial. Binomial and geometric random variables. What does binomial imply? 2. And so binomial, there's going to be 2 outcomes. We either succeed or we fail. So, like a coin toss, we might say heads is succeeding, tails is failing, so we either succeed or we fail. There's no other options in here. you're trying to decide whether or not you've been given a situation where you want to say that this is a binomial random variable, you need to, I don't know, our notes use this weird acronym, like they spell out binomial and make that important. I didn't learn it like that. I learned it as bins. So we learned how to cuss. We have some other cute acronyms overlap, but today's acronym is bins. So if you're thinking something's binomial, you need to check the bins. You need to check if it's binary, meaning you can either succeed or fail. You need to check if it's independent, so each trial is independent of each other. So just because I got heads last time doesn't mean that it affects whether or not I get heads or tails this time. You need to check the number. There needs to be a fixed number of trials. Like they tell you in the problem, we're going to flip the coin 30 times. It's not an endless coin flip. They tell you how many times they're going. And you need to check the success rate. All trials should have the same probability of success or failure. So like with a coin flip, 50% chance, success or failure. So you need to check the bins. Okay, and then we call the expected value we've been trying to calculate, we call that the counted success in a binomial setting. And then we actually call the probability of it a binomial distribution. And there is some notation if you want to know, and I swear it's not really, I don't know, I guess you have to know how to read it. They might put B meaning binomial, then they might put like 6, and then 0.5, N being number of trials, and P being like the probability of success. And if you knew that, you can make a distribution as well if asked for different values. Okay, so that just sounds crazy, so we just need to practice an example. So, Alex, you were good at reading yesterday. Will you read this one?
Determine whether or not the given random variable has a binomial distribution. Justify your answer. Genetics says that children receive genes from each of their parents independently. Each child of a particular set of parents has probability 0.25 of having type O blood. Suppose these parents have 5 children. Let X equal the number of children with type O blood.
Okay, so let's stop for a second. Let's deal with part A. We need to determine whether or not it has a binomial distribution. So we're literally going to check the bin. You know how when it was for your fonts from chapter 1, and I would count off if you didn't cuss fully? Like if you left off the U, I would count off. Or if you left off on the S's, I would count off. Same thing's going to happen with the bins. If you don't check all the parts, the binary, independent, number, and success, you're going to get counted off. So we've got to check the bins. Okay, I'm probably going to do it like a lazy man. Do we know for sure that we can, is it like classified binary? Is it going to be classified in 2 ways, success or failure?
Yes. So either have O type or not.
Yes, so it's either O type, not O type. Okay, what about the I, the independent?
So if it's not binary, do we just stop?
Yeah, well, if it's not binary, I would probably try to do some of the stuff we did yesterday. Binary is going to be like a special case. Like if binary, do this. If it's not binary, try to do some of the stuff we did yesterday. Yes. Binomial, say, yes, sorry. Binary, binomial, all the same. Not really. But okay, I for independent. Do we know if it's independent?
Yes.
How do we know that?
Yeah.
It says the phrase is given. It says independently in there. Okay, are we given a set number of trials?
Trials.
Yeah, because we're given the number of kids. There needs to be a set stopping point. That's what we're looking for.
I don't like that. Oh, you like giving birth trials? Yeah.
Yeah. For this one, it is funny. And then S for the success.
It calls the kids trials.
We're looking to see all trials have the same probability of success or failure. Do all the trials have the same probability?
Yeah.
Yeah, kids
As
fail a
long as they're
lot.
the same thing.
Yes.
I'm one of them. Because they all just,
All have same parents. I like that.
I would argue that they don't have the same probability of failure. Because me and Luis are brothers, and he's a lot more successful than I am.
Well, but
Yeah.
theoretically, you know, from one child to the next, like just because one had brown hair doesn't mean sure the next one's gonna have blonde or the next one will have brown. Like there's stuff like that, including blood type. It's supposed to be
Yeah, we
Completely
just have different
When in
moms.
different.
Punnett square it
I
out.
mean, it's close.
Yeah. Okay, so we've determined that it is a binomial distribution, and we've justified our answer by showing the different parts of the bins. Could I write this out nicer? Absolutely. Probably with complete sentences and everything. But seriously, all I'm looking for when I read through your answers, the same way when I read through to see if you passed, is did you do the bins? So, part B. Go ahead, Alex.
Shuffle a deck of cards. Turn over the first 10 cards one at a time. Let Y equal the number of aces you observe.
And before we do that, let's back up to the last one, because we need to clarify success. Because we can be more specific than that. Yes, they do have all the same parents, but we're actually told some other stuff.
And they're either O type or not.
They told us numbers.
I mean, yeah.
I have children.
They told us a percentage. We should
Yeah.
probably reference that to show that we're smart.
No.
They said the probability of success, 2 C's, success, is 0.25 per child. Or per each trial if you're cool with children in trials. So this would be better for our S because we're referencing back to the problem. Plus, they literally did tell us that. Although making the argument they have the same parents, we should have the same probability of success is a good point. Okay, so if we were to put it in that notation of B n comma P, the B, the number of trials was 5, the probability of success is 0.25. Okay, now finally for real ones B, which Alex read about the deck of cards. So let's check the bins on the deck of cards. Okay, is it binary?
Yes, either you get an ace or no.
Yeah, so it's either, so success would be you get an ace. And if I wasn't trying to fit in a lot of stuff, I would, no, I'll fit it in. Failure,
Why don't you just do it, brother?
no ace. I don't know, it's like once you're committed to something, you just gotta roll with it, you know? Is it independent?
I don't think so. Because if
It doesn't say.
also just like the
Alright.
fact if you have 10 cards and you don't replace the card or anything like that, then there's less and less of a chance of getting an ace. Or if an ace, you know what I'm saying?
Mm-hmm.
It probably changes every time you look at the observer card.
So, the first card we draw is a, well, there's 52 in the deck, right?
Yeah.
And how many aces are there? 4. But the first card we turn over, it's just 1 out of the 52. But he's right. The second card we turn over, since we didn't replace it, we're now on 1 out of 51. And so technically our odds are changing each time. The next card, we've got a 1 in 50. Really, we've got a 4 in 50. It depends on did we turn over an ace or not. So, but our probabilities do decrease since we aren't replacing the card. The next card is least. If the first card you turn over is an ace, the next card's not likely to be an ace. So no. Trials are not independent. Now, like Louise is saying, if they had said that we're replacing each time, then it would be. But because we're not replacing the cards, and every card we draw means there's one less in the deck, the trials are not independent. So we can stop there. We don't have to complete the bins. Once one of the letters fails, we can call it a day. Finally, Louise's dreams come true. Alex, will you read part C?
Shuffle a deck of cards. Turn over the top card. Put the card back in the deck and shuffle again. Repeat this process until you get an ace. Let W equal the number of cards required.
Okay, so still got to check the bins. One could argue the B is just like last time. I'm just going to draw an arrow to what I said last time. Success, get an ace. Failure, don't get an ace. Are we technically independent this time with our different trials?
If you're replacing it and rejecting
So if it's independent, you can go on what the enemy has.
Yeah. You know, once one letter fails, why bother? You're like, it failed. It's not binary. So, yes, because replacing card and shuffling deck. I need to stop using it. And then in the number of trials.
I don't know, yeah, it doesn't specify, so I guess no. I mean, it says let W equal the number of cards, but it has to be the number of trials. But, or no, would that be the total, like, you're pulling from? Total pool you're pulling from? Is it like the 52?
No, I think W is the number of cards you're required to get.
Yeah, like I had to pull out on the 13th card, I finally got my ace. On the 13th draw, I finally
So
got my ace.
would that work or would you not?
Still, yeah. it
Am I
doesn't specify.
necessarily ever going to get the ace?
Well, yeah.
I mean,
Eventually, yeah.
Yeah, eventually, yeah.
the book argues the number of trials is not set in advance. You could get an ace on the first card, or it may take many cards to get an ace. Because there is no fixed number of trials, this is not a binary setting. Not a binomial setting. Binomial. So, I'm with you, but technically, they need to be very specific if we're doing this 10 times. Or we're doing this 20 times. So they've got to be no, because there wasn't a fixed number of trials. But could one argue on one's paper, if you were facing this setting, that technically N is met because inevitably I must reach the ace? I guess so, if you have some math to back it up. Okay, so we talked about how to check the bins and to see whether or not a given random variable can be classified as a binomial random variable. But then what? So we actually need to calculate probabilities the way we calculated probabilities when it was a discrete or continuous random variable. Which leads to the next little bit, how to calculate the probabilities.
Do one after two? Or, this is, I mean, every time you go shuffle it anyway.
One would think so. One would think so. Okay, so if you know the number of arrangements of k successes, which sounds crazy, I swear there's a better formula in just a second, but this is the part I want to focus on, t to the k and 1 minus t to the n minus k. So, let's say I did 10 trials. I had 3 successes. And I had a 25% chance of being successful. Then looking at the last part of this formula, the p to the k, well, I had a 25% chance of success. My number of successes were 3. But it makes sense that if I failed 3 times, if I succeeded 3 times, that means I failed 7. And it also makes sense that would be a 75% chance, because if I'm failing, it's going to be an opposite percentage of my chance of success. So while that formula looked like a hot mess, it kind of makes natural sense. I'm going to raise the probability of success to my number of successes. I'm going to have the probability that I fail raised to my number of failures. Okay, so how do we find this C in the front? It's put in parentheses because it looks like a hot mess. How to find this? It's called the binomial coefficient. Like, it's so important it has a name. It's called the binomial coefficient. And your notes say we can approach this in one of 2 ways. When I read that, I thought they were pi, but they're not. I thought they were crazy because I have always done the formula way I'm going to show you. You you are not a formula person and you never really liked permutations or combinations anyway, then there is a second method I will show you momentarily. But I like formulas and I like factorials, and the formula made sense to me, so I was a formula person. Okay, so you can use the formula for the binomial coefficient. There I did it again. So, back to our fake example I just made up. If we knew we had 10 trials, so maybe n is 10, and we had 3 successes, it ends up being the combination formula, which in the combination formula you put your number of trials in the numerator as a factorial, and you put your number of successes and failures in the denominator. And the denominator always adds up to the numerator, because 3 plus 7 is 10, so that makes sense. So if we had 10 trials and we succeeded 4 times, well then we stank it up 6 times. The good part is you don't even have to necessarily remember the formula. You just need to remember that when it comes to the part in front, you're going to need your calculator, because your calculator can calculate this for you if you tell it you're doing a combination. So if you have your calculator, I know that we normally live on the stats button because we're in stat class. But technically lately we've been doing a lot of probability problems, so we need to go to the probability section. There's not a button that says prob. Why stat gets to be cooler and have a button, I don't know. To get to this on your calculator, you need to press math. You scroll over to prob, and then literally you're going to see a button that says NCR. The capital C means combination. That's what we're doing. So math, scroll over to prob, third one down, NCR. Now before you press it, I actually should tell you we have to hit it in a certain order. So for instance, on my fake example that I've made up, you have to hit your number of trials, then the NCR button, and then your number of successes. So for us, I'm going to press 10, then go to this NCR button, and then press 3. So on my calculator, I press 10, then I press math, scroll over to prob, go down to NCR, and press 3. And my calculator calculates that coefficient for me. So your note says that there are 2 ways to do this. Really, one can argue 3. There's, hey, I actually know and understand the formula. Or, hey, I'm like Hunter, and I really like calculator buttons. I can remember this button. The only issue with remembering the button is that if you press NCR before you type in the number of trials, it's going to let you down and make you think you're crazy.
What was the buttons?
Math, and I scroll over to prob, and it's NCR. It's the third one down. But you have to put the number of trials first, so like 10 first.
What was the original ratio?
The original ratio.
Yeah, that thing.
Oh, so if you actually wanted to work this out with your factorial self, you know factorial means you count down. So 10, 9, not 10 more. 10, 9, 8, 7, 6 factorial is going to cancel out with the other 6 factorial. 4, 3, 2, 1. 4 and 2 go into 8. 3 goes into 9 3 times. So I still get 21 times 10, so I still get 210. But again, that requires you doing some math by hand.
That was 120.
I pressed the buttons wrong. Oh, I did the wrong problem. Look, I did my 10 4 6, not my 10 3 7. Aren't I supposed to be doing the 10 3 7?
It's 5 factorial anyway, so.
So if I did that one, 10, 9, 8, 7 factorial, 3, 2, 7 factorial. The 7s cancel out. 2 goes into 8 4 times. 3 goes into that 3 times. I did 4 times 3 times 10, which really is 120. I did the wrong one, my bad. But yeah, you get the same number either way. Now again, I'm more likely to make a calculator button mistake, so I'm a formulaist. Hunter's more likely to make a formula mistake, so he's going to calculate it. There's still a third option for those who don't like to do this. Yes, dear.
Is the problem always going to save the trial, or we have to do
It's always going to say how many trials.
Okay.
Why don't you still let that Pascal?
I don't like that either. When I've Googled the best out of it, it doesn't have the extra H. Okay. Now, so Shalia came in here yesterday morning and was asking about a problem in your book that involved flipping a coin 4 times, heads and tails. The number of successes was based on heads. She actually could have used this binomial trick because we're checking the bins. And it's equal chance of heads or tails. Success and failure is going to work out. She had a set number of trials. Once we listed them all out, she did. The independent, well, yeah, heads and tails are associated. And the probability of success is the same each time. It's not going to change. Like, just because I got heads one time doesn't mean it changes the next time. So she technically could have done this problem using this. Instead, I made her make a list and physically list out all the options. So if you really, really, truly got stuck and you had like 20 minutes to kill, could you actually list out all the options of all the heads and all the tails and all the things? Yes, you could. Pending your number of trials is small. We'll use this. Yes, dear.
Okay. You've probably already answered this. I just have to double
No.
check. How will we know when it's a combination? How will we know it's a permutation?
We have not had to do any permutations yet. It's our first time to run into either with any factorials or anything. Just know if you're dealing with binomial coefficient combination. I don't know. That's the only way I got it. Combination coefficient.
In ACT prep, we had to do, or I had to do.
But you know permutations is when the order matters.
Yeah, that's what I was about to ask. I
Right.
just need to double check
But
that.
technically our order doesn't matter right now.
But like if it was a first, second, third place thing, it would
Yes.
be a permutation.
Yes. But then there's a yes.
I remember this second.
Okay, so here's the thing that I didn't know, and we're going to work on the next problem and prove it works. But here's the thing I didn't know involves Pascal's triangles. So flip to the back of the next page, and it actually shows you a picture of Pascal's triangle. It's about midway down, 3/4 way down. So if you know the number of trials, you can actually use Pascal's triangles to figure out that binomial coefficient. And it's really crazy, and you're like, why the crap does that work? But after we work our next example, we'll reference back the triangle and see that it did work. If you wanted to know the triangle, it's not a bad thing to know in life. The first row is 1, the second row adds up to 2, third row adds up to 4, 8, and then it ends up being 16. It ends up, so it's 1, 2, 4, 8, 16. If we did the next row, I bet it's 32. And it always ends up being that pattern. The middle number always ends up being a bit larger. If you draw it out the diagonal, notice there's a 1, 2, 3, 4. The first one's all ones. Maybe you would remember this. Never in my life did I know this was going to work for this. If we're being honest, that's not how my teacher taught me. I didn't know it would work. But it does work. So if you would rather, like somehow you and Pascal can have a common Jesus meeting and you understand Pascal's triangle, you wouldn't have to use the formula at all. You could just use the triangle.
Did you draw that on Mr. Ward too?
No. Do a what?
Mr. Ward had a first name.
No, I did not.
Yeah, he does.
So Shalia's example, do you still have those mini post-its too? Probably not.
Oh yeah, I think
Okay, that's fine. Shalia's example was dealing with, you had, the probability of success was of getting a heads. So we discussed it could be 4 heads, or it could be all tails. And then we ended up listing out like pairs of heads. And we ended up listing out all the options with 2 heads. It ended up being 4. And it ended up seriously, I didn't tell her this at that time, and I should have. It ended up seriously being row 4 Pascal's triangle. So she said, because me and her were trying to figure out how many trials were there total, because in this specific problem you weren't told, she was supposed to figure that out herself, which I understand, again, in binomial they're supposed to tell you the number of trials. But like you're arguing with but you could argue with the coin toss, especially, well, there were 4 trials. We were counting the ways of success. I guess there was a set number of trials. There were 4 trials. We were just arguing the different probabilities of
Miss
success.
Thompson?
Yes, ma'am.
Is Shalia Johnson in there?
Yes, ma'am.
In a couple of minutes, tell her she can head to Miss Johnson's room.
Yes.
And Miss Brown's room.
Yes, ma'am. Thank
Okay,
you.
thank you.
So she was wanting to know, like, how many total options were there. And we came up with a set number. She said, how could we have come up with that number without listing it out? And we could have used this triangle, or we could have used the formula. Okay, I don't know how I got on that page. Moving back up to the top. Okay, I don't know if you know this. Maybe you don't know this. 0 factorial is 1 in life. The factorial symbol means we count down to 5, exclamation points, 5, 4, 3, 2, 1.
Why is it done? Why is it 1?
Because we don't know anything. If we do times 0, then everything's 0.
I mean, yeah. So
Why bother to list the 1? I don't.
So why is 0 factorial 1?
Why is 0 factorial 1? Why is this God?
I mean, that's the answer. But why is 0 factorial 1? Like, your question.
It's completely legit messages. Anyone know why 0 factorial 1?
Wait, what did you just say?
Why 0 factorial 1? I don't know. Has anyone ever actually used 0 factorial?
No. Why is it? Wait. How is it?
I mean, it would make sense for 0 factorial to be 0. Why is 0 factorial 1?
I mean, people look at
You know what I never understood? How come something to the 0th power is 1?
I used to know why. I forget though.
Because, you know, when we
To the
do,
first power.
you know, 2 to the 3rd really means we're doing 2 times 2 times 2. So 2 to the 0 means we really don't have any 2s.
Means
That if
Huh?
they have
Right,
if
no,
there
yeah,
are
I get what
twos,
you're
why
saying.
wouldn't it be 0? The question is, you know, if there are no 2s, why wouldn't it be 0?
I hate her.
I forget. There's a whole proof.
I love
There's a whole proof with it, yeah. There's a whole thing. There's this whole thing. So I used to think there used to be a positive and negative 0. No one really explained why to me. There wasn't a positive or negative 0. To be honest with you, 0 is my favorite number because 0 is so freaking complicated. Like, how can you 0? How? Why do you confuse me? I can answer everything else in life until it comes to you, 0.
how come we don't
Me
include
too.
0 factorial?
I don't. Well, I
It's
mean,
zero in
It's
the
your
factorial.
more
I mean, 0 factorial is just 1, I guess.
it is a rule. I mean, yeah, it is a rule, but surely it came from something as to why it is a rule.
Yes.
That's how rules got made.
I feel like if I had a really smart person explain it to me, I still wouldn't get it.
No, I had a really smart person one time explain how we they derived the quadratic formula from a square, and it was I don't ever want to ask that question again.
Yeah, 10 factorial.
You don't want to know. I promise you.
Do
You
you
don't.
remember it?
Yeah, it was not
I'm
handed
saying
over here.
since it's included. Why?
Yeah, we got some time.
Oh, yeah, I see what you're saying.
Oh no, we do. Let's finish our one problem, and then we can go with the time. Okay, so
Wait, Miss Compton.
yes,
Okay, she has an actual valid answer.
yes.
Because so in a factorial, whenever it's when each step of the factorial, it's like so 10 factorial is just 10
Then
times
on
9
eight.
factorial and so on.
Right.
So 0 is included, and I think the reason that there's a law that is 1 is because with 0 included, if it was 0, then every factorial ever would be 0. But since it's 1,
Oh, that makes sense.
I mean, yeah, but I still.
I guess that's why they made it, because that was fact. Like, you know, everyone always asks me, like, why do we do 5, 4, 3, 2, 1, not 5, 4, 3, 2, 1, and 0? I'm like, my papa 0, and the whole thing's 0, and it's stupid. But so that makes logical sense. That okay,
So
I don't know,
that
I'll-
was to
that still
eliminate
makes sense
the
to me
zero.
because in
That
that
makes
case,
sense.
That is
so
what
just
you're saying.
include like negative
I
numbers,
understand why that's
and that would
now.
make it like different. I'm assuming they just don't include it for the fact of not including it.
right.
So,
Because like 5, 4, 3, 2, 1, 0, negative 1, negative 2. Like, how did you know when to stop?
so they would just not include it, not to include it,
also
right?
2 plus 2 is 4, 2 times 2 is 4, and 2 squared is 4.
This is how it
Isn't
works.
that curious?
That upsets me so much.
Isn't that so curious?
Because like 3 plus 3 is 6, but 3
But
cubed
and you
is
see people know stuff
27.
because they put 4 for everything, and then you ask them like 3 cubes, and they're like, "Oh, is it still 9?" No, it is not 9. Thank you for trying. Okay, so moving on.
We did that thing that we do all the time.
I know. With each child. Okay, so we have this formula that we're supposed to remember theoretically. That the binomial coefficient is the n factorial over k factorial n minus k factorial, and then we're still going to want to raise our probability of success to the number of successes, our probability of failures to the number of failures. To me, the second part of the formula makes perfect sense. Probability of success raised to successes. Probability of failure raised to the number of failures. But I digress. Okay, so it says each child of a particular set of parents has probability 1/4 of having type O blood. Suppose the parents have 2 children. let X equal the number of children who have type O blood. Let the sample space of all possible outcomes using letters S and F for success and failure. Okay, so I don't know why I wrote the formula. We don't actually have to do the formula quite yet. So let's do, it says sample space of all possible outcomes using S and F. So success and failure. So we could have, since we have 2 kids, we could have 2 successes. We could have 2 failures. Success then failure. Failure then success.
Why is it a failure to not have type O blood?
Because we're just, that's how they decided to label it. You know, again, we got to be binomial, we have to have success and failure. Okay, so, but what's interesting is that while these 2 are in a different order, it's technically 1S, 1F, so they're really the same thing. So again, back to Pascal's triangle, it's that 3rd line down. Because there were 2 trials, we're technically on row 2. 2 S's, 2 F's, the SF, and the FS. So it's just really curious to me. So if you wanted to use Pascal, you can. If you want to be like me and just list out options, that's fine too. Okay, so we want to show the probability that neither children have type O blood. Okay, so for the N choose K, we know there were 2 trials. And I guess this is why they just mentioned 0 factorial, because of this issue right here. If neither children have type O blood, then we have 0 with type O blood.
Yeah.
And then so we had 2 with other types of blood. So technically that binomial coefficient, we normally put how many trials are in the numerator, how many successes and failures, they should add up to the number of trials. 0 plus 2 does add up to 2. And that explains why we had to go with stupid 0 factorial. Okay.
But yeah, I looked it up. So basically, like, factorial just means the different ways you can arrange a number. So like 1 factorial, you can only arrange it one way. 2 factorial would be 1 and 2, or 2 and 1.
0 factorial, they're honor of the ranks.
Exactly. So that's why apparently it's 1. And then also, when you set it up with the equation, you said it was like n it was like 1, crap, no. It was like n times n minus 1, and then n would be 0. And you set it up to equal 0 factorial, it would equal 1. Or 1 factorial. You set it up to equal
I hate
that.
this problem.
He has some truth in this because, okay, back to in discrete, I got off track, but in discrete we've been dealing with stuff like if there are 5 seats, how many ways can we put the different people in the 5 seats? Well, there are 5 options for the first seat, but once someone sits down, there are only 4 options for the second seat. When someone else sits down, there are only 3 for the next, 2, and then 1. So it makes sense what he's saying if we're backing it up to that. Go on, dear, she's waiting on you. Okay, getting not distracted.
Oh, don't switch.
Back to this. Yeah. Back to this. We found our binomial coefficient. However, we've still not done, it was n factorial, k, n minus k, p to the k, 1 minus p to the k, 1 minus p to the n minus k.
I hate this formula.
The probability of having a success, they tell you in the problem, it's a probability of 1/4. So 1 out of 4, so a 25% chance that we have type O blood, which means there's a 75% chance we don't have type O blood. So if you want to change that to 0.25 and 0.75, I totally understand that. I was just going with fractions because they gave it in fractions. Now our number of successes for this first part, we didn't have any with type O blood, which means we had 2 with non-type O blood. Okay, so does anyone have any questions about how I got the 1 for my binomial coefficient?
I know it's my key. I got look for.
Okay. Yes,
Everyone's a little
I know, but we gotta get this done. Okay, so this was our formula. This junk right here is me calculating the 1. It goes in the front of the formula.
Anything to the 0th power is 1.
Right.
I remember that.
Is everyone cool with the 1/4 to the k, 3/4 to the 2? The 1/4 of the k is that nobody had type O blood. The 3/4 to the 2 is 2 of us had not type O blood.
It looked like
Okay, so he's right. Anything to the 0 is 1, and then 3/4 to the second, it's just going to be 9/16. So I need to know whatever 9/16 is as a decimal to tell you my actual percentage.
0.75.
No, I got 0.56.
Oh, well, I assumed it was 3/4.
So there's a 56% chance that neither have type O blood. But I mean, back to that must make sense because apparently You're only in 1 in 4 chance of having type O blood, so the odds of 2 kids both not having it, that's pretty good. Okay, so we did with 0 successes. Now we have to deal with 1 success. There are still 2 trials, but we've had 1 success and therefore 1 failure. So our coefficient is going to be 2, because 2 over 1, that ends up being just 2. So our binomial coefficient is 2. There's still a 1/4 chance of us having type O blood. We had 1 kid with type O blood, 1 kid without it. So I'm going to do 2 times, I get 0.375, which is about 38%. So there's about a 38% chance that we're going to have one of the 2 with type O blood. And then the last one, we said, what are the odds of having both kids with type O blood? So still, there are 2 trials. Maybe they both have type O blood, which means neither of them have the other. So our binomial coefficient's again a 1. We had 2 that were successful. We had no that weren't type O bloods. So I'm just doing 1 times 1/4 to the second, which ends up just being 1 over 16, which is 0.0625. And because I'm a good math student, and we realize in life we're genius, we've evaluated all our options, what should the purple, green, and red add up to?
1.
And if they don't add up to 1, then we've done something wrong, so they better. There's always potential for rounding error.
You know. Well, yeah, on the first one.
I get 0.9975 because I rounded. Okay. So is there anything to you about that? I like that. We'll come back to,
Can you explain like the quadratic formula thing you're talking about?
yeah. We'll come back to the bottom one tomorrow, but I seriously like binomial. If you check the bins and it works, this one actually ends up being pretty cool. I should stop the recording. The world does not need to know.